Crash Course Instrumentation, Episode 34, Hands-on Ohm's Law with Batteries and Resistors. Now that we've explored voltage, current, and resistance conceptually, it's time to get hands-on. In this episode, we'll break out some real-world tools, batteries, resistors, and a multimeter to measure and visualize Ohm's Law in action. The setup. We'll start with a basic circuit. A DC power source, like a 9-volt battery. A known value resistor, e.g., 1000 ohms. A digital multimeter set to measure current and voltage. Step 1. Measure voltage. Across the resistor, place your multimeter in parallel with the resistor. You should read around 9 volts, minus any internal resistance in the battery or contact loss. Step 2. Measure current through the resistor. Now set your multimeter to current mode, amperes, and place it in series with the resistor. With a 9-volt source and a 1000 ohm resistance, Ohm's law predicts intensity, amps, equal volts, divided by resistance, equal 9 volts divided by 1000 through ohms, equal 0.09 amps or 9 milliamps. Try it with other resistors. Use a 470 ohm or 2200 ohm resistor and observe how the current changes. As resistance increases, current decreases. As resistance decreases, current increases. Simple, beautiful, and reliable. Polarity tip. Be sure to connect your multimeter properly. Backward leads won't damage the meter, but will result in negative readings. Meter modes. What changes? Voltage, V, and resistance, U, are measured across a component. Your meter stays in parallel and doesn't change the circuit's behavior. Current, A, is measured through the component, meaning you must break the circuit and insert the meter in line. This requires more care and is why current measurements can be trickier in fieldwork. Pro tip. Many technicians prefer using clamp meters to read current, especially in AC systems, because they're safer and quicker than breaking a circuit. Linear relationship. When plotted on a graph, the voltage and current relationship for a resistor is a straight line. This tells us the component obeys Ohm's law. The slope of that line is the resistance. This is why resistors are called linear devices. Resistors are also what is known as a passive electrical device. This simply means a resistor doesn't need any outside signal or source to make it operate, unlike, say, a transistor. Other passive electrical devices include the inductor and the capacitor, both of which we will discuss in depth in later episodes. So please hit that like and subscribe to stay up on the latest episodes. Current versus voltage source. In most circuits, we use voltage sources, like batteries or power supplies, but it's helpful to understand that current sources also exist. These deliver a fixed current regardless of the resistance in the circuit. Specialized test gear and sensor simulators often use this concept. Why this is important. 1. Technicians use these tests to validate sensors and circuit behavior. 2. Troubleshooting often involves confirming whether voltage drops or current draws are within expected ranges. 3. Proper meter setup is a basic but essential field skill. 4. Understanding how and where to place your meter is just as important as the value it displays. From theory to practice. Ohm's law isn't just academic. It helps us design safe circuits, calculate fuse ratings, size components, and validate loop integrity. A historic impact. During the development of the telegraph in the 1800s, engineers relied heavily on Ohm's law to determine how far they could transmit signals using copper wire. Without this understanding, early long-distance communication networks like the transatlantic telegraph cable, completed in 1866, would have been impossible. Ohm's law wasn't just theory, it shaped global infrastructure. Next time, we'll dive into real-world resistor markings, tolerances, and how terminals and wiring affect what you see on your meter. Like, share, and subscribe so you don't miss episode 35.